Why is this beautiful, distant, unknown so alluring? Scientists are plagued by questions. If we assume the universe is limited in volume, does it have boundaries? Can we reach them? What does the edge of the universe look like? Let's start with where we are now and try to look as far as we can. Beyond 100,000 light-years, the Milky Way ends. Beyond that will be an ocean of galaxies, possibly 2 trillion in total, and that's just in our observable universe. Their types, shapes, sizes, and masses are diverse. But as we look further and further, we begin to notice something unusual. The farther a galaxy is, the more likely it is to be smaller, lighter, and its stars will be bluish. This makes sense in the context that the universe had a beginning, a birth. Looking back in time, the early universe. The birthday of the universe is the Big Bang. A galaxy relatively close to us will be close in age to the universe itself. But if we look at a galaxy billions of light-years away, the light from it must have traveled for billions of years to reach our eyes. A galaxy whose light would take 13 billion years to reach us would be less than 1 billion years old. Therefore, the farther we look, the further back in time we are looking. Thousands of galaxies are at immense distances from us and from each other. However, it's not possible to see with the naked eye that every galaxy has an associated spectrum where a gas cloud absorbs light of a specific wavelength, depending on the atom's physics. As the universe expands, wavelengths stretch, so distant galaxies appear redder than they actually are. This physics allows us to determine their distance. And when we determine distances, the farthest galaxies turn out to be the youngest and smallest. Beyond galaxies, we expect to find the first stars there, and then nothing but neutral gas because the universe hadn't had enough time to pull matter into a dense enough state for stars to form. Millions of years ago, the radiation in the universe was so hot that neutral atoms couldn't form, and photons continuously bounced off charged particles. When neutral atoms formed, light simply traveled in a straight line forever, subject to nothing but the universe's expansion. The discovery of this afterglow, the cosmic microwave background, CMB, over 50 years ago, was the definitive confirmation of the Big Bang, the evolution of the universe, and the limit of observation. Today, 13.8 billion years after the Big Bang, there are stars and galaxies in their current form. Earlier, galaxies were smaller, younger, and less developed. Before them were the first stars, and even earlier, just neutral atoms. Before neutral atoms, there was ionized plasma, and even earlier, free protons and neutrons, spontaneous creation of matter and antimatter, free quarks and gluons, all the unstable particles of the Standard Model, and finally, the moment of the Big Bang itself. Looking further into space means looking further back in time. Although this defines our observable universe, with the theoretical boundary of the Big Bang located more than 46 billion light-years from our current position, this is not the real boundary of space. Instead, we simply have a boundary in time. There's a limit to what we can see because the speed of light has only allowed information to travel that distance in 13.8 billion years. This distance exceeds the same 13.8 billion light-years because the fabric of the universe has expanded and continues to expand, but it's still limited. Beyond the Big Bang, cosmic inflation. But what about what was before the Big Bang? What would we see if we could somehow look a tiny fraction of a second before the universe reached its peak of highest energy, hot and dense, full of matter, antimatter, and radiation? We would see that the concept of cosmic inflation existed when the universe expanded very rapidly and was dominated by the energy inherent in space itself. Space expanded exponentially during this time, when it was stretched flat, when it had the same properties everywhere, when the fluctuations of quantum fields inherent in space permeated the entire universe. When inflation ended, The hot Big Bang filled the universe with matter and radiation, giving rise to the part of the universe, the observable universe, that we see today. 13.8 billion years later, we are here. But it's worth noting that there's nothing special about our location, neither in space nor in time. The fact that we can see 46 billion light-years away doesn't make that boundary or sixth location special. It's simply the limit of what we can see itself. The infinite cosmos. If we could somehow take a snapshot of the entire universe going beyond the observable part, we would see the same thing that our universe has: a cosmic web of galaxies, clusters, filaments, and cosmic voids extending far beyond what we can see. Any observer in any region would see exactly the same universe as us. The individual details would, of course, be different. There would be a different solar system, galaxy, local group, and so on. But the universe itself is not limited in volume. Only the observable part is limited. It is the boundary in time, the Big Bang, that separates us from everything else. We can only approach this boundary with telescopes that can see the early universe and with theories. Until we figure out how to circumvent the forward-rushing flow of time, this will be our only approach, our way to see the edge of the universe. But the cosmos is boundless. Well, guys, I hope you enjoyed the episode. There was much to fantasize and think about. So comment if you have anything to add, and don't forget to subscribe if you're not with us yet. We have many interesting journeys ahead. For now, best wishes to everyone, and see you in new episodes. This is interesting.